Hello, Justin. You can start. Introduce.
Okay, it's a pleasure to introduce Michael Turner from the University of Birmingham to talk to us today. So he's going to talk about skew axial algebras of monster type. Over to you,
Hey,
Michael.
thank you very much. Can everyone see my slides just to make sure that they're all working? Yeah, cool. So I'm going to talk about some of my research that I've done on skew axial algebras of monster type. So I'm going to start by firstly defining what an axial algebra is for anyone that doesn't know what it is. And then I'm going to then start talking about what it means for an axial algebra to be skew. With that all done, then I can introduce some skew axial algebras, show some examples and show that they do exist. And then hopefully at the end, be able to classify them all. Okay. So for an axial algebra, we need something called a fusion law. So this is just a set and a binary operator where the operator doesn't go back into the set, it goes to element in the power set. And we call this pair a fusion law. Throughout the talk, I'll probably refer to a fusion law just by the set, kind of like a group or a field. And with a fusion law, we can grade it by a group. So we have this group T and a fusion law F. We can grade it by having a map, Ski, which takes an element from the fusion law to an element in group. And we have this property that for lambda mu in F, we have Ski lambda times Ski mu in this group multiplication is equal to Ski mu, where mu is mu is an element of this lambda star mu. So lambda star mu, remember, is a set. So we've got to check it for each element in this set. One thing I haven't written on this slide is that we want the grading to be such that we have that the image is equal to the group. We kind of, every fusion law we can grade to the trivial group. So we kind of want some nice grading so that we have a non-trivial grading to look at. Okay, so one of the main fusion laws that pops up in axial algebra theory is called the Jordan fusion law. So it's a fusion law with 3 elements in its set, 0, 1, and eta. And the binary operator star is defined as followed in the table. We omit the curly brackets. And so if we've got an empty entry, then that means it's equal to the empty set. So maybe to clarify, 1 star 1 is equal to set containing just the 1 element. And eta star eta is going to be the set containing 1 and 0. This fusion law is C2 graded. So we have 0 and 1 will go to the identity element of C2, while eta will go to the non-identity element of C2. This is called a Jordan fusion law because it's a generalization of the fusion law of Jordan algebras, which were constructed in the 1930s, I believe, and are heavily related to quantum mechanics. So the next one, which is going to obviously appear in the talk because it's in the title, is the monster fusion law. So this is a fusion law with 4 elements in its set now, 0, 1, alpha, and beta. And we always want our fusion law to have elements that are distinct. And maybe just to make a note, this monster fusion law has a Jordan fusion law inside of it with just the 0, 1, and alpha. If we just look at 0, 1, and beta, we almost get another Jordan fusion law. However, we've got this alpha appearing in beta star beta. This is, again, a C2 graded fusion law, where 0, 1, and alpha go to the identity element, while beta goes to the non-identity element. This is called the monster fusion law, as it's a generalization of the Greece algebras fusion law. If we wanted to look at the Greece algebra, alpha would equal a quarter and beta would equal 1/32. And the Greece algebra has automorphism group of the monster sporadic group. Okay, so those are the fusion laws that are going to pop up in this talk. And so let's kind of get ready to define an axial algebra. So I'm going to let bold F be any field that I'd like, and let capital A be a commutative algebra with small a being in the algebra. we have the adjoint map, which takes element x and we multiply it by a. The adjoint map, we don't need to care about left and right adjoints because we're in a commutative algebra, so they're going to be equal to each other. We're going to let spec A be the set of eigenvalues of the adjoint map of A. Maybe just a note to say is that I may get a bit sloppy with my notation and say eigenvalues of A or eigenvectors of A, but I actually mean an eigenvalue of the adjoint map, because this is going to be is a map rather than A being just a vector. Okay, so then the next one is, well, for a lambda in our field, we want to denote the lambda eigenspace of the adjoint map of A by A sub lambda of little a. And if we're looking at a subset of the field, we want a S of A just to be equal to the direct sum of all the lambda eigenspaces of A, where lambda is in S. Okay. So with this, we can now define some special elements in this algebra, which are called axes. So we've got this fusion law F, A being a commutative algebra over the field, and little a being in this algebra. We call A a primitive F-axis if it satisfies 4 properties. So firstly, A squared is equal to A, so A is an idempotent. Secondly, we have that the whole algebra is decomposed into the lambda eigenspaces of A. Further, we want that all the eigenvalues of A are contained in the fusion law. So the third property, we start to introduce what our star binary operator does interacts with this algebra. So what I'm saying is, if I take a lambda eigenvector of A and a mu eigenvector of A and multiply them together, I want them to be contained in some certain subspace. And we have it as the subspace of lambda star mu. Lambda star mu is going to be a subset of the fusion law F, so it may be a direct sum that we're looking at over there. And finally, we have that the one eigenspace of A is just one-dimensional. It's only going to be the linear span of A. So yeah, if we don't assume the fourth condition, this is a non-primitive axis. However, I'm going to assume all axes are primitive. So from now on, when I say axis, I mean a primitive axis. If it is not primitive, then I will specifically say it's non-primitive. And with this, we can define an axial algebra. So again, we've got this fusion law F, we've got a commutative algebra over the field, and now we've got this set X, which is just a collection of F-axes in A. We don't need to take the whole set of F-axes. We can just take as many as we want, or as a few as we want. For this talk, we're for this talk, it's going to be X is going to have a cardinality 2, so we're only going to take 2 axes. And we call the pair AX a F-axial algebra if X generates A. It's important to note that if I take two, if I've got X and I've got Y, and they're both generate A, and they're both a collection of F-axes, then AY may have a different fusion law to AX. So we've got to be very specific on what generating set we're looking at and what fusion law we're looking at. And this is going to be clear later on why we've got to be pretty specific on what we're doing. Okay. And kind of the final definition in axial algebra theory that we're going to use is that we can create automorphisms in our algebra. So from now on, I'm going to let the characteristic of the field not equal to 2. We're going to assume that F is a C2 graded fusion law with gradient map Skew, and yeah, we're a 2-generated axial algebra AX. Okay, so if we take a F-axis A, we can define a map tau A, which goes from the algebra back into the algebra, and we define it as follows. So if we have a eigenvector, a lambda eigenvector of A, this tau map takes V to itself if the grading takes lambda to the identity element in C2 and minus V if it doesn't. And it's why we want the characteristic not equal to 2, because this would just give us a trivial map to look at. And in fact, this definition extends the whole algebra, because we've got that the algebra is decomposed into eigenspaces of A. And yes, so we call this tau map the Miyamoto involution of A, and it's also an automorphism of the algebra. Maybe just a quick note is that automorphisms will take f-axes to f-axes. All the properties of being an f-axis is preserved under the automorphism. Okay, so I've talked about axial algebras, but I haven't actually told you that they do exist. So I was going to give you some examples. Actually, just before then, if we have the Jordan fusion law, then the tau map acts as the identity on the 1 and 0 eigenspace and negative identity on the eta eigenspace. And if we have the monster fusion law, then the tau map will act as the identity on the 1, 0 alpha eigenspace and negative identity on the beta eigenspace. Okay, so yeah, now on to some examples. So let us have a look at a three-dimensional axial algebra. So we've got this basis of x, y, and z, and we've got the following multiplication. If we take two elements in x, y, and z, a and b, I want the multiplication to be as follows. If I multiply a and b, I want it to equal a if a is equal to b. So basically, I want x, y, and z to be idempotents. Further, if a does not equal b, I want it to equal the following: eta over 2 a plus b minus c, where c is going to be the third element that I've not picked. So if I was doing x times y, then c would equal z. This is a two-generated axial algebra of Jordan eta type. And it can be generated by xy or xz or yz. Any two will do. And we denote this by 3c eta. Something that will pop up later on in the talk is that we're heavily relying on something having an identity. So if eta does not equal -1, then this algebra has an identity, and the identity is 1 over eta plus 1, x plus y plus z. If eta does equal -1, then there is no identity. It's got an annihilating element, which will also pop up later on, but the construction will be a bit different. And maybe just remark that this is an example of a Mutsau algebra, which are constructed by the free transposition groups. So for anyone that doesn't know, a free transposition group is a group generated by a constancy class of involutions in which the product of those involutions have order at most 3. So in the 1970s, Fisher classified the almost simple free transposition groups, and he got that the symmetric groups pop up, a few examples, a few families of matrix groups popped up, and also there were 3 new groups that popped up, which were the Fisher groups, and gave us 3 new sporadic simple groups. So for 3c eta, this is the Mutsau algebra on the symmetric group of 3 letters. So we take the group S3, and we have the constancy class of involutions is, well, the only constancy class of involutions in S3. Okay. So another algebra that's going to pop up is Q2 1 over 3. So these algebras were constructed from looking at subalgebras of Mutsau algebras by Joshi in, I believe, 2020. So this algebra can be as a basis of S1, S2, D1, and D2. Multiplication is defined in the table. So this is a two-generated axial algebra of monster type 2/3, 1/3, and we can generate it by S1 and D1. For the SI elements, this is actually going to be a Jordan, a third axis in the algebra, while the DI elements are actually going to be monster 2/3, 1/3 axes. Again, we've got to think about identity later on. So in characteristic not equal to 5, this algebra does have an identity. And when the characteristic does equal 5, it doesn't have an identity. It's going to have an annihilating element. And we've got this nil ideal S1 plus S2 plus D1 plus D2. And taking the quotient, we get another new algebra, which is Q2 1/3 cross. This is also an axial algebra of monster type 2/3, 1/3, and it's also 2-generated. Maybe just note, this is just one algebra of a family of algebras. If we take 1/3 to be any beta, then we get a axial algebra of 2-beta beta monster type. However, they're not going to pop up, so I've only defined this algebra. Okay, so hopefully I've convinced that axial algebras do exist. And so we're going to take a turn now to something called axets. So axets were defined by McInroy and Spektorov in 2021. However, they did do some work beforehand with something called closed subsets of axes, I believe. So this is a completely group theoretic definition, and you could study axets without looking at axial algebras. However, using axets with axial algebras is very fruitful and helps us understand the structure of an axial algebra. So for the axets definition, so we have two groups, S and G, and we're going to let G act on a set X. We're also going to have a map which takes an element from X and an element from S and maps it to G. And for ease of notation, we kind of use Tx of Txs is equal to T sub X of S. Then the triple G, X, and tau is called an S-axis, S-axet, if it has 3 properties. So the first two tell us that for any X, our tau X is going to be a group homomorphism from S to the stabilizer of X in G. And the third property tells us how the group action and conjugation interact with each other. So again, if we know what G and tau are, and it's quite clear what they're going to be, then we're going to denote this axet by just the set X. And also we're going to define T of X to be the image of all the tau X maps. And this is called the axial subgroup corresponding to X. So yeah, maybe just note, these axets completely group theoretical. So I believe examples are obviously any group action, you can probably produce an axet, but also root systems pop up in axets. Another thing that we kind of want to look at is, well, it'd be nice to have a closure, sense of closure and also generation of these axets. So we have this triple G, X, and tau be an S axet. And we say a subset of X is closed if Y is invariant under all its TY maps. So what I do is I've got this set, and if I keep applying my tau maps, no new elements pop up. I'm always going to stay in Y. And we can also define what closing means. So we have this set Z, which is a subset of X, where we can define the closure to be basically the smallest closed subset containing Z. So again, kind of, you could also think of it as taking Z and just keep applying tau maps, see if any new elements pop up, add them to the set, and then keep applying that until no new elements pop up. And if we've got a closed set, we can say it's K generated if it basically we can generate it by K elements. So let me tell you how axets and axial algebras coincide with each other. So if we have an axial algebra AX with fusion on F, and F is going to be C2 graded, if we take just every F axes in A and take the group to be the automorphism group of the algebra. Then we can define tau x of E to be the identity map, and tau x of S to be the Miyamoto involution of X, which I defined a few slides ago. Well, then this triple is going to be a C2 axet. However, looking at all f-axes in our axial algebra is quite a hard task for some algebras. Sometimes there's infinitely many, and sometimes we don't actually know how many axes there are. So it'd be kind of useful to start with our generating set rather than looking at everything. So the second example says, well, let's start with our generating set X, and let's just make it Y the closure of X. So just keep adding, keep applying the tau map until no new elements pop up. If we take H to be the set stabilizer of Y in G, and tau prime to just be the restriction of tau to the domain Y C2, then this is also going to be a C2 axet, and it's kind of much more manageable C2 axet to look at. Further, because we're looking at two generated axial algebras, this is going to be a two generated axet because X is two generated, so Y has to be two generated as well. And these are going to be the axets that are going to be useful to look at when we're looking at two generated axial algebras of monster type. Okay, so let's look at some examples of axets. So firstly, we can look at, say, let X be this regular n-gon, and look at the vertices on this n-gon. Well, the group of this n-gon is going to be just the dihedral group of order 2n. And we can define a tau map to basically be the identity if we've got tau A of E. And if it's tau A of S, then we just say it's going to be a reflection of the regular polygon at the vertex A. This is going to be a two-generated C2 axet. And we can take the pair two adjacent vertices to generate the whole axet. We can then take this to the extreme and look at x infinity. So this is going to be a straight line. So we just got a number line, an infinite number line. Then the group is going to be the infinite dihedral group. And we can then just take tau A of E just to be the identity map, and tau A of S to be the reflection of X at that point. We're just going to reflect the number line at that point A. Again, this is two generated. Just taking two adjacent points will do to generate the whole axet X. These two examples are something called a regular axet. And now I can then talk about what it means for an axet to be skew. So we're going to start with a regular 4K gon, where K is going to be an element of natural numbers. And we've already got a axet of D8K, K4, X4K, and then the tau map from the previous slide. What we're then going to do is we're going to look at one bipartite half of the polygon. So we can label all the vertices by, say, the integers, and then look at the even indexed vertices. Well, there's going to be vertices that are opposite each other in the even set. And what we're going to do is say that they're going to be equal to each other and carry on doing that for each pairs of vertices in the even half, identifying them. Well, then this is going to be a new axet. It's going to have 3K vertices now, because we've identified half of the even vertices to each other. And we denote this by x prime k plus 2k. The group now is going to be a dihedral group of order 4k, and we're going to take tau prime just to be the restriction of tau to the new domain. So to illustrate this, I've put in the figures for x prime 1 plus 2 and x prime 2 plus 4. So we start with a square for for k equals 1. And what we do is we identify the top and the bottom vertex together. So this is now just one vertex A. We don't do anything to the odd half of the bipartite polygon. So B and C are just going to stay the same, and we're not going to say they're equal to themselves or anything else. For k equals 2, we start with an octagon. And again, we're going to label the top and the bottom by the same vertex A, but also we've got the left and the right one because we've got now 4 elements in the even bipartite half. So the left and right one are going to equal each other. So this, and again, we're not going to say B is equal to C or B prime or C prime. They're going to be distinct vertices. So we start with 4, say k equals 1, we got 4 vertices and now we're down to 3. And for the octagon, we start with 8 and now we're down to 6. For the rest of the talk, we're going to mainly focus on this first skew axet. And maybe just to reiterate that this tau map of A is going to switch B and C about. However, the tau map of B and the tau map of C, because they're going to be equal to each other, won't swap any elements in this axet around because it theoretically will swap A with A. However, that's just going to be the identity map. Okay, and these are 2 generated C2 axets, and we call these skew axets. And so if we have an axial algebra, we can find an axet through the generating set X, and I'm going to be focused on when this axet is going to be skew. So McInroy and Spektorov in 2021 actually classified that these were the only 2 generated C2 axets possible. We either have XN, so a regular axet, or we're going to have this skew case. So this is quite useful because this basically tells us if we want to classify, say, the 2 generated axial algebras monster type, then their axet is going to be either regular or skew. So it'd be kind of useful to kind of classify the regular ones together and then classify the skew ones together. And then, in fact, if we have both of those answers, then we've got we've got the complete classification for these 2 generated axial algebras of monster type. Okay, so now I'm going to talk about some examples of skew axial algebras of monster type. So what I'm going to do is throughout this section is I'm going to use a trick of twisting an axis by its identity. So taking an axis and going identity minus that axis and making that a new axis. So we're going to start with 3C alpha, and we're going to assume alpha is not equal to -1 or a half. We're not assuming -1 because it doesn't have an identity. And we're not going to assume alpha is equal to half because this won't actually produce a skew axet. So we're going to discount that as well. So we've got this basis x, y, and z as before. And we have this identity element 1 over alpha plus 1, x plus y plus z. So what we're going to do is we're going to twist this x by its identity. So we have w is equal to the identity minus x. Now, this is now no longer a Jordan alpha axis, but it's now a Jordan 1 minus alpha axis in A. Again, if we do this twisting argument, there's W will always be an axis. However, its fusion law will be different depending on what fusion law you start with. So this algebra A can be generated by W and Y. So it's a 2 generated axial algebra. And it's also got a fusion law of our monster alpha 1 minus alpha. Okay, since Y is going to be a Jordan alpha axis, its tau map is now trivial. It was non-trivial when we were doing Jordan type 3C alpha, but now because we've got a monster type and we've got monster fusion law alpha 1 minus alpha, this tau y is now trivial because it's got no beta eigenspace. However, W is going to have a non-trivial Miyamoto involution because it is a Jordan 1 minus alpha, so it's got a beta eigenspace. Okay, so one can find the eigenvectors of W, and further, if you just then apply the Miyamoto involution of W on Y, you'll get it equal to Z. And this is going to be an axiogra of that skew, and it has the axet x prime 1 plus 2. So maybe just to reiterate where these axes appear in the axet, we have that the W goes at the top and bottom, and its tau map is going to switch Y and Z about. However, the tau map of Y is going to be trivial because it's going to swap W with W, so nothing happens. And again, tau map of Z is going to equal tau map Y. To avoid confusion with this new algebra, because we're starting with both A's, however, we've taken different generating sets and we've got different fusion laws now. We're going to denote this new algebra by 3C alpha 1 minus alpha when it's got this fusion law monster fusion law alpha 1 minus alpha, just to avoid confusion if we're looking at an axial algebra of Jordan type or an axial algebra of monster type. Okay, so when alpha does equal to a half, we can't do our identity trick because we don't have an identity to start with. However, what we can do is cheat a bit and start with a different 3C and produce an axial algebra of monster type -1, 2. So we start with 3C2, and this does indeed have an identity element of 1/3 x plus y plus z. I'm still using the same basis as when I first defined 3C. Well, what we can do is we can twist the other elements by the identity. So instead of x, we twist y and z about. And this is also going to be a two-generated axial algebra generated by x and u this time. We can assign the algebra, the fusion law monster -1, 2 now, as x is going to have fusion law Jordan 2. That's because that x is what we started with. And now u is now going to be an axis of Jordan -1 because we've done this twisting identity on this y element. And the rest follows as before. We can look at the Miyamoto involutions of both u and x and figure out what happens. And this is going to be a skew axial algebra and has axet 1 plus 2. So again, just a diagram to kind of explain myself a bit more. We start with x here, and we've got u and v. The tau map of x swaps u and v about. However, the tau map of u and v does nothing. It's going to act as the identity. And again, we're going to denote this 3C2 with this monster fusion law by 3C -1, 2, just to avoid confusion because we've got the different generating set. However, the same algebra pops up. And maybe just a quick remark is that if we were looking at 3C alpha 1 minus alpha, where alpha doesn't equal -1, we do in fact get that these opposite vertices actually produce the whole algebra. However, for this algebra, we don't in fact get that. This becomes the algebra generated by u and v is actually the two-dimensional quotient of 3C -1. This pops up later on in the proof, but this is quite an interesting remark. So the next thing is looking at our Q2 1/3 and trying to see if we can do the same argument as before. So we're going to assume the characteristic of the field is not equal to 5. And we've got the algebra as before, Q2 1/3, basis multiplication as defined probably 10-15 minutes ago. We have an identity because we're not in characteristic 5. The identity is going to be 3/5 times S1 plus S2 plus D1 plus D2. Now we can then twist the D1 element by the identity. So we define T1 to be equal to 1 minus D1. And now this is going to be an axis of monster 1/3, 2/3. So before, D1 was an axis of monster 2/3, 1/3. So we've basically swapped alpha and beta around. One can show that this is going to be a two-generated axial algebra generated by S1 and T1, and now has a fusion law monster 1/3, 2/3. So the tau map of S1 is going to be trivial because it is a Jordan 1/3 axis, so there's no beta eigenspace of S1. However, the tau map of T1 is now non-trivial because we've now got a axis of monster 1/3, 2/3. So the beta eigenspace is the non-zero space subspace. Okay. So again, we can look at and find out what the eigenvectors are, and then with this we can prove that if we take tau map Miyamoto involution of T1 and act it on S1, this is going to equal S2. And this is going to produce another skew axial algebra with the same axet x prime 1 plus 2. So to just reiterate, we've got this diagram. So T1's at the top and bottom, and then the tau map of T1 swaps S1 with S2. However, the tau map of S1 and S2 is the identity. And again, to avoid confusion, we're going to denote this new algebra because we've got a different generating set and also a different fusion law by Q2 1/3, 2/3, just to avoid any confusion on what generating set we're starting with. Okay, and finally, we've got another algebra popping up when we have characteristic equal to 5. So this is slightly different because when we start with the quotient Q2 1/3, this doesn't have an identity. And to get around that, we just basically add the identity element into the algebra. So we've got this three-dimensional quotient, and we basically just add another dimension with an identity element. So yeah, so Q2 1/3 quotient is generated by x and z, and it's spanned by x, y, and z in the table below. And then we just add this new identity element, which has multiplication of an identity element. So maybe just note x, y are both Jordan 1/3 axes in the quotient Q2 1/3 x, while z is going to be a monster type axis of 2/3, 1/3. So now we've got this identity, we can actually do our trick again. So let W be 1 minus z, where z is, remember, a axis of monster type 2/3, 1/3. Well, then W now is an axis, and it's now got a fusion of monster 1/3, 2/3. We can then show that A is going to be two generated and generated by X and W, and it has the fusion law monster 1/3, 2/3. Again, tau X is going to be trivial because it's going to just be a Jordan 1/3 axis, so it's got no beta eigenspace, so Miyamoto involution acts trivially. However, for the W1, because we've got this beta eigenspace, it's not going to act non-trivially. It's going to act non-trivially. So again, we can find out what the eigenvectors of W are and show that taking the Miyamoto involution and acting on X, we get Y. And so I didn't put a diagram here, but we've got W at the top and bottom, and then X and Y on either side of that square. And this is another axial algebra that is skew and has axet x prime 1 plus 2. So with this, you may be starting to think, okay, we can now take an axial algebra and make it skew. However, that's not going to be the case. So if we're given an axial algebra with an identity, it is true that if we take an axis A and twist it by the identity, so A prime is equal to 1 minus A, it is going to be an axis. However, there's a few things that we need to check. Firstly, A prime is most likely, well, almost certainly going to have a different fusion law to what A started with. And also, it may not be primitive, because if we have the one eigenspace of A prime, this is equal to the 0 eigenspace of A. However, if the 0 eigenspace of A is, say, 2-dimensional or more, then the one eigenspace of A prime is going to be 2-dimensional or more, and so it's not going to be primitive. So we've got to be very careful on when we twist this do this twist with the identity, that we actually stay a monster fusion law, especially if we've got other elements that we need to generate with. We need to make sure that the fusion laws are compatible with each other, and so we don't get anything bigger than the monster fusion law. And also need to check that it is primitive, because yeah, it breaks down if we've got a large 0 eigenspace of A. Okay, so with that, we can give a classification of all skew axial algebras of monster type. So I'm going to assume that the field is not characteristic. The field has characteristic not equal to 2, and K just being an actual number. So we're going to set it up so AX is an axial algebra that's 2 generated and of monster type, and we have an axet X in the angled brackets is going to be isomorphic to a skew axet X prime K plus 2K. Well, then, in fact, K has to equal 1. And either we have, and basically we have all the algebras that I've described in this talk today. We have the 3C alpha 1 minus alpha, where alpha and beta have to equal 1. And then we've got this kind of sporadic case that pops up when alpha and beta is equal to 1/3, 2/3. Either it's going to be this Q2 1/3, 2/3, if the characteristic is not equal to 5, and then if the characteristic is equal to 5, then we take the quotient and then add the identity. So just to give you a flavor of how I managed to prove this, I had to basically split it into 3 parts. So in my first paper, I looked at K equals 1. So let's assume A is a 2-generated axial algebra with a skew axet X prime 1 plus 2. Then we can take B without loss of generality, B to be the tau map of A switches B with C. So the first task was to find a spanning set for this algebra. And thankfully, using work of Clara Franchitti, Mariam Andrus, and Sergei Spektrov on their papers of 2-generated primitive axial algebras of monster type. They've done 2 papers, a general one, and then alpha is equal to 2 beta. I can use some of their equations to restrict the dimension of A to be at most 4, and also get a complete multiplication table. Second bit was to use something called Serre's lemma. So certain fusion laws we can say when elements associate with each other, and that's was proven by Serre's. So with that, I was able to produce some equations with constants, so alpha and beta pop up, but also some constants concerning something called a projection map. So if you're in a primitive axial algebra, there's something called a projection map, which basically tells you if you have a element in A, then you can kind of just project it down to the one eigenspace and look at what element of the field you have for that. So yeah, using Serre's lemma, I was able to get some constants to help me. And then the final bit of that was, and the main part of it was looking at U being equal to the 2-generated axial algebra of Jordan type alpha, and going through each possible U and see what happens and see if anything pops up. So these two generated axial algebras Jordan type were classified in 2015 in the sister paper of when axial algebras were first defined. And so it's just looking through these possible U's and seeing if anything pops up, and thankfully only the examples popped up. So for k odd and k greater than 1, then we kind of look at two subalgebras of this large axial algebra of Skew with Skew axet. Firstly, we take we have this subalgebra which actually has Skew axet x prime 1 plus 2. And we've also got another subalgebra, an axial subalgebra, which is going to be symmetric and have axet x 2k. So a symmetric, two generated symmetric axial algebra is an axial algebra where you have the generated set, say x and y, and you've got a automorphism that swaps x and y about, and it's going to have order 2. And this is called the flip automorphism. So these symmetric axial algebras all being classified for monster type, thanks to Yabe and also Clara and Mario. And with our restriction that alpha plus beta actually has to equal 1 for every Skew axial algebra, and we've got the classification of the symmetric algebras, then actually there's not a huge amount of options that we can have. So firstly, k has to be 3. If k is greater than 3, then beta has to equal 1/2, and we can't have alpha and beta is equal to 1/2. So there's only a few cases to check, and no new algebras pop up. For k is even, then kind of like the odd case, we have we can find a subalgebra with a Skew axet. However, this, instead of 1 plus 2, we've got this 2m plus 2m plus 1. So basically the largest power of 2 that divides k. And then there was just some work around, and well, quite a lot of work on understanding the structure of an axial algebra if it did have axet x prime 2m plus 2m plus 1. And in fact, they don't exist. So we've got this subalgebra that doesn't exist, so the whole algebra can't exist. And with these 3 cases, this gives us the complete classification of these Skew axial algebras. And yeah, I think that's everything I want to say. So thank you very much for listening.
Thank you very much, Michael. Are there any questions from anyone? There is a question in the chat. Michael, can you see that?
Yes.
Perhaps start with that one.
Yes. So the Jordan algebras have a fusion law of 1, 0, and 1/2. So the Jordan fusion law is kind of a generalization where eta, we take et, so if you take et to equal 1/2, then we've got this fusion law of Jordan algebras. So yeah, this Jordan fusion law is just a kind of a generalization of that fusion law. Does that make sense? Okay.
Yes. Are there any other questions?
Hi, Justin. Here is Mario.
Hi.
I just have a comment. I think Michael forgot to quote you as one who contributed to the classification of the symmetric algebras.
Oh, I'm very sorry, Justin.
That's okay. Any other comments or questions? I've got a couple of questions. If not, do you know what the automorphism groups of these algebras you found are? Are they all just an S3?
I imagine the 3C is going to be S3.
Yeah. But the other one, of course, isn't, is it? No. The other one's probably a V4, Klein 4 group.
Possibly. I haven't actually checked, but hopefully Josh's PhD thesis or the paper hopefully gives us some idea on what that automorphism group is going to be.
Yeah. Actually, I think I could find out for you if you don't know, but yeah, run some code on it and find out. Also, in terms of the way you've gone about proving this,
Yes.
it seems like there's a couple of different things which have gone into that. So you need to know a classification of the symmetric ones, and then a number of your other steps seem fairly seem like they might extend to a different fusion law, perhaps. So if I gave you a different fusion law, the same sort of proof strategy could work for that. Suppose we know the symmetric two-generated algebras, then this would be a way of going about finding the non-symmetric ones.
Yeah. I feel like there's going to be some work in finding out the spanning set of these algebras. That may be a bit difficult. But yeah, as long as it's series, we can find probably some equalities or constants. Yeah, and just looking at subalgebras, that should be fine. Yeah, I feel like there could be a possibility to generalize, but there's probably going to be a bit of work to get around that.
Yeah, that's nice. And do you know any larger algebras, so not two generated, any 3, 4 generated algebras which contain these two generated subalgebras?
Yes. So I've been looking at binary axial algebras, and if you have, so you've got 3 pairs of axes and say A prime, B prime, C and C prime, then if you have characteristic equal to 11, a 4b between A and B, so a 4b 1/3, 2/3, and then B and B prime and C prime give us that Q2 2/3, 1/3.
Okay.
Then that will be a axial algebra with a skew axet inside of it. I am working on seeing if any other axial algebras, because the 2b is kind of the thing that needs to be used. And I am looking at seeing if the X4 two-generated axial algebra is trying to classify them all to see if any other axial algebra can be put there. So we're not in this characteristic 11 case, but they do appear, but they're probably quite rare.
So that example, did you say that was actually one of the other symmetric examples, but you've just found a non-symmetric set of axes inside it in characteristic 11?
What the binary example or Q2?
Yeah, the binary example. So you've got 6 axes, 4 of them are a 4b.
Yeah.
And does everything end up inside that 4b, or
no? So it's going to, so that's 5-dimensional. I believe it's going to be 6 or 7-dimensional, I think.
So it really is properly 3 generated. Yeah.
Yeah, it will be 3 generated.
Great. That sounds really interesting. Yeah. Does anybody else have any other questions? Well, if not, let's thank Michael again for that excellent talk.
Thank you.
Thanks very much, Michael. That was, yeah, really enjoyed hearing about that.
Great. Well, thank you for listening.
Yeah, no, lots of things that I started thinking about like a bit in lockdown and didn't have, didn't have time, didn't get to, didn't all the rest of it. But yeah, no, really good that, really exciting that we've actually got some results here.
Yeah, in fact, I didn't really talk about it, but if you take Q2 to be a third beta, then you're going to get a fusion law, which is going to be kind of the extended monster fusion law, which is kind of interesting.
So
like five elements.
Okay.
And I think if you look at some of the symmetric algebras, you can do kind of a twisting thing, and that possibly will give you some extended monster fusion law. That's going to be Skew as well. But there's still quite a lot of work if you want to try and classify them all.
Yeah. No, it's interesting because the 1 minus, like the identity minus construction, so in the split spin factor algebras, that switches the two classes of idempotents.
Yeah.
And I happen to know, but I don't think anybody else does. Well, at least I told Sergey a couple of times, but every time I've told him, he's forgotten the last time I've told him that the 4B algebra is actually isomorphic to one of Yabe's 4Y algebras. It's just you switch the two classes of idempotent. So the 1 minus the idempotent switches the two classes. So that twisting by the idempotent is
okay.
So they're isomorphic as algebras, just not as axial algebras.
Okay, yeah.
Yeah, because it's turning an alpha beta algebra into a beta alpha. Oh, sorry,
1 minus alpha,
a 1 minus
beta.
Yeah, that, yeah. Yeah, so it's interesting that same construction, if you like, is sorry, I'm looking at you here because you're over here for me. That same construction is doing the like twisting, but for one of the sets or for some of the axes. Yeah. So you're always, so this is true for the 3C, that it can be generated by two of them, and as a monster type algebra, those two generate, but they're actually closed because you're taking them as, so then, and is that the same for the Q2 one, that you've got a generating set of, well, not quite a generating set, that doesn't matter, it's just that the fact that they're only, because they've got to have no beta part, those are the ones that you're twisting.
Yeah.
Right?
So in fact, if you have a two generated axial algebra monster type where one is just a Jordan alpha and the other one can be whatever axis, then it's going to be the whole algebra is going to be either these Skew examples or just Jordan alpha type, because that's the only way that they can work.
Does the 3 and more generated case, does that feel more restrictive than when you're trying to build algebras from just symmetric algebras? Is it just more restrictive because you've got to have, any intersections are going to be two B's, like you said, but well, actually, is the Q2, is it two B's in the Q2 as well?
So in Q2, you've got the S1 subalgebra is going to be 2B.
Yeah.
And the T or the D, whichever T or D you want to look at, that's going to be a 3C subalgebra.
Ah, right, okay.
So you've got that. So if we're looking at the free generated case, it's going to be a 3C, and then 2B, where you have these two being the Q2.
So you've got 2s and 3s.
Yeah.
That sounds good to get large amounts of algebras. And you've got 3C alphas, you say. So yeah. Oh, but 3C. Okay, 3C alphas, not 3C betas, 3C alphas.
Yeah.
Okay. So you, okay. So maybe you've only got 2s to join in like an axet to be acted on.
Yeah, probably.
2Bs, yeah. That's still, okay. Maybe that's doable to classify them all then. Or to get some.
Yeah, I mean, you can make, so with that kind of example, what you kind of want is